Okay, so this will be a very short video because it deals with a topic known as indicators. Indicators are substances which, excuse me, take on a particular color based on the acidity or basicity of its environment, right? So the first thing I want to mention here is that indicators are, generally speaking, weak acids or weak bases. So we can use this to represent what happens hypothetically when an indicator is added to water. It's a weak acid, and it basically dissociates to form H plus and the corresponding conjugate base, right? And typically what happens is that the color of the undissociated molecule will be different from the color of the conjugate base that is formed from it. And this is where you get into a situation of color changes when the pH changes, right? So basically, if you add acid to this mixture here, according to Le Chatelier's principle, it's going to shift to the left, and therefore the solution will have mostly this molecule, the undissociated molecule, and therefore the color of the solution will be predominated by the color of this undissociated molecule. On the other hand, if you add base, which removes this, then the equilibrium will shift to the right, and therefore the solution will be mostly this, so therefore the solution will take on the color of the conjugate base. So that's basically how indicators behave, all right? Generally speaking, if the ratio of the undissociated molecule to the conjugate base is greater than or equal to 10, then what you'll find is that the color of the undissociated acid will predominate. On the other hand, if the color of the undissociated, the concentration of the undissociated molecule divided by that of the conjugate base is less than or equal to 10, then it is the color of the conjugate base that will predominate. And therefore, what you see in the table below are different indicators and their colors in acid and base, right? So for example, thiamine blue will be red in acid and yellow in base, right? And there's a pH range for all these indicators over which the color change will take place. So therefore, in the case of thiamine blue, the color change will start taking place from a low value of the pH of being equal to 1.2 to the high value of 2.8. So in other words, in acid or in pH situations below 1.2, the color of the thiamine blue will be red. But above 2.8, it's going to be yellow. All right, so that's basically how you interpret the pH range. All right, okay. And this is just basically giving you a picture of dyes isolated from cabbage and the different pH values or pH ranges correspondingly with the colors. So basically, the dye in cabbage can actually behave as indicators as well. All right. Now, this is the reason why indicators are important when it comes to titration of acids and bases. We're going to look at the example of the titration here between a strong acid and a strong base. And we're already familiar with the shape of that curve. It looks like this, where the equivalence point is about 7, right? So you'll notice that there's a pH increase, significant increase from about pH 3 to about pH, I would say 12, right? So that's where the pH increase will take place, right? Where the equivalence point is smack in the middle of, right? So therefore, any indicator that you're going to choose to indicate the equivalence point must experience a pH range, color change within that range from 4, I'm sorry, what did I say? From 3 to about 12, right? So that's the reason why we could not use thiamine blue, right? Because thiamine blue color change does not occur within that range. If we had used thiamine blue to indicate the equivalence point, then based on the experimental results, the equivalence point would come too early because you would observe the color change here, whereas the equivalence point is much further, right? So therefore, the indicators that are useful for indicating the equivalence point would be methyl red and phenolphthalein. These two indicators, as you can see here, experience their color change within the pH range of the pH jump of this titration from 3 to about 12, all right? So it's very important that you choose the correct indicator to accurately reflect where the equivalence point is. So based on what we have just learned, you should be able to answer this question. This question says, which indicator would you use for titration of nitrous acid, which is a weak acid, the equivalence point will be somewhere above 7 because the resulting solution will be basic whenever you're titrating a strong base versus a weak acid. So therefore, of all these indicators that you would use here, the ones that you would choose to indicate the equivalence point of this titration would be let me just skip all this here. So as I said before, the pH is greater than 7 at the equivalence point, and therefore the indicators that you would choose for indicating the equivalence point would be cresol red and or phenolphthalein. Any one of those two would be useful for indicating the equivalence point of such a titration. All right, because in both cases, the pH color change ranges for those indicators would be above 7, right? 7.2 to 8.8 here, and phenolphthalein, which is 8.3 to 10.0. All right. Okay, so that basically is it as far as indicators are concerned. So the next topic we'll be discussing is solubility equilibrium when it comes to ionic compounds. Until next time.